Good morning, students. Excuse me. Good morning, students. Good morning. I'm expecting a reply. Good morning. Okay. So, can you all hear me? Huh? Is it clear? Just put it in the chat. Yeah, it's clear. So, if I am not audible to you all, just let me know in the chat box so you can interrupt me at any time. And occasionally, my camera uh, changes its view. It's 38 students. Uh, so this thing. Yeah, a lot of students actually registered for it, like 100 students. But the time is the problem. But I will be uploading the recording. So by any chance, if the connectivity is not good, you can also use the recordings. And you all most probably know my YouTube channel. I mean, if you are a Tamil speaking student, so this IP, I will not be uploading my video to this channel. I will be uploading this recording to the channel Roshan Akhtar. Okay, so this is like a physics only channel, so it's like being developed. It doesn't have much subscribers, but it has more subscribers. I will be uploading to this channel. Okay, so so let's start. So I'm Roshan Akhtar, fourth year medical student, University of Colombo. Uh, I'm also teaching physics. Usually I teach for Tamil medium students. This is the first time for teaching English medium students, like in a common class like this. So let's start the session because it's like 8:03. We are supposed to start this at 8. So let's do from 2009. Okay, we are going forward. So 2009, 45th question. Usually this subunit of humidity related things is a nightmare for the students, isn't it? So let's read and see whether we can solve this. Yeah. When a person wearing spectacles moves from room P to Q, he observed that a thin film of water is deposited on the lenses. So consider the following that are given as necessary conditions for this to happen. So they're giving a scenario. That person is moving from room P to Q. Okay, so let's draw. But you are not supposed to draw when you are doing such a question because you are there literally wasting time. But for explanation purpose, I'm just drawing. So this is room P, this is Q. So that person is moving from P to Q, and he is observing. He's observing a thin film of water getting deposited on his lens. Okay, so have you ever seen film of water getting deposited on glasses in any advertisements? Those who watch cable TVs or even in the Sri Lankan advertisements, it's shown. What advertisement? Which is well known for showing the formation of water films on the glasses. Like dew, it's called dew, not literally water, dew. What's the advertisement? What's the product? You don't know? Answer. So shall I like ask individually? Like Afra Salman, do you know of any advertisements? Yeah, have you ever watched close-up advertisements? Huh? That's all. So, so in that advertisement, they go and exhale on a glass surface, and then they draw whatever they wanted to. So that particular occasion is similar to this occasion. Okay, that particular scenario. So what happens there? Actually, when you like exhale, you have a fair amount of water vapor in your exhaled air. So that air, that water vapor actually gets saturated near the surface of this glass. So it actually gets deposited on this glass. So that's what you observe as dew, okay, or water film, okay. So why does that happen? Because the water gets saturated. So what is getting saturated? Saturated means like the water, the water vapor cannot remain in the form of gas, so it becomes liquid. So it happens when the RH, relative humidity, is 100%. So that is actually when the water vapor is saturated. So you can actually saturate the water vapor in two ways. What are those ways? One is related to the density of the water vapor, or the mass of water vapor. The other way is related to the temperature. So what can you do to the density? Should you increase or decrease? Just answer this is the easiest question that can be asked. Huh? To saturate the volume, what should you do? To increase the density or decrease? Is it obvious? Huh? Just tell. Hello, students, please. What do you think, Amina? Yeah, the density should be increased. No, density should be increased. And the temperature, what should you do? You should decrease the temperature so that it reaches the dew point, and then you see the water vapor getting saturated. Okay, so these two are the two possible ways of making unsaturated water vapor into a saturated water vapor. Okay, so now what is the possible option here? When the person is moving from P to Q, there is less likely that this thing happens. No, the density of water vapor increases. That's less likely to happen. So we can actually assume that the temperature reduces, so that the Q, the water vapor in the Q, gets saturated and deposited on the glass. Okay. So how can that happen? Now think. So this is the glass of the spectacle that the person is wearing. So now this spectacle is somewhat cool. Okay, it's like cold. It's a cool one in relation to this room cube. The temperature is low. So that's what that is meant by being cool. Okay, cooler when compared to the cube. So what happens? It absorbs heat from the surroundings. So the temperature of the surrounding air reduces. So eventually it reaches the dew point. So then what happens? Then that observation happens. The water vapor gets deposited on the surface of the glass like this. So here the unsaturated one became saturated, isn't it? Due to the reduction in temperature. So what's the condition? What's the fundamental condition that should exist here? That particular glass should be cool. It should be cool. So where did it come from? This glass, it came from the P. So the room P should be cooler than the Q. So the objects in the particular room are also cool. So when they come here, they absorb the heat from the surroundings and the water vapor becomes saturated. So that's a possible scenario. Okay. But just think, for that particular temperature, for the temperature of the glass, this scenario didn't happen in P. So what's the reason for that? The same thing didn't happen in P because the density of the water vapor is not enough here. So to get deposited, there should be water vapor. Okay, adequate amount of water vapor should be there to get deposited. But here it's inadequate, and in Q it's adequate, so that in the particular temperature this scenario happens. So what can you tell about the density of water vapor here? So it is density of water vapor is called absolute humidity, AH. So AH and AHQ. Can you just compare these two? Which is greater than which? Just think about it. Huh? Answer. Otherwise, I don't feel like talking to human beings. I mean, I don't get that feeling. Huh? Can you answer that? Ambika Lingeshwara, can you answer this? What do you think about densities, age? Come up with something, please. Please. What can you tell about age? So AH is adequate here, no? So it should, the AHP should be less than AHQ. Okay. So that condition should also be there. There should be adequate amount of water vapor here, so that to that particular temperature, the saturation thing occurs in Q, but not in P. Okay, when he was in P, but he didn't observe such a thing there. But when he comes here, he observes such a thing. So A should be greater in the Q room. Okay. So this is the thing. So these are the possible conditions that you can come up. First condition is this, and the fundamental condition is the temperature. So temperature of P should be less than the temperature of Q, so that when it comes here, it cools the surrounding air, and the things that have been mentioned happen. Okay, so now they are giving statements. So A, temperature of room P is greater than the temperature of room Q. Please ensure that you all have muted your microphones, because I can hear an echo. Echo is coming from one of you. Yeah, now it's okay. So temperature of room Q is greater than the temperature of P. So that is correct. A is wrong, B is correct. And relative humidity of room P is greater than the relative humidity of room Q. So you can actually predict the AH of these two rooms, but not RH. Why? Because RH is expressed like this. RH is equal to AH over AHS into 100. Okay, so AHS means the density of saturated water vapor. AH means the density of the water vapor there now. 100 is for the percentage. So this AHS and AH differs for these two rooms, P and Q. So okay, for example, if we take AH is greater in Q. But what about the temperature? Temperature is also greater in Q. So when temperature increases, you know the AHS increases. Okay, so let's understand like this. In higher temperature, you need more and more water vapor to saturate a volume. In higher temperatures, you need more and more water to saturate a volume. Why? Because saturation happens when they cannot maintain their kinetic energy to be in the gaseous state. But automatically, if you increase the temperature, they get adequate kinetic energy to remain as gases. So for higher temperatures, you need to give more and more water vapor to saturate the particular volume. So this one increases with temperature. The temperature is the only determinant of AH. Okay, AH is like whatever that is there. Okay. So AH is comparable, AHS is also comparable, but when you consider Q, both are high. When you consider P, both are low, but you don't know about the ratio. Okay, you cannot actually predict about the ratio. So you cannot be very certain about RH, but you can be certain about AH. So that statements about RH are not very much clear for us, so we can't take them as correct. So the one and only statement that's correct here is B. Okay, am I clear? Do you have any doubts? If you have any questions, you can put in the chat box. I will check frequently, okay, so that I can answer. Yeah, there are 17 messages in the chat. Maybe you were telling answers in the chat. Bro, do you recommend? No, actually, because 22 students can do some questions, but okay, P greater than Q, high in P. Yeah. Just unmute and answer because I can't check very frequently, no? I will check. I can't check very frequently, but I will check. I will be checking. But I would prefer if you all can answer using the mics. Okay, not chat boxes. The next question is also from thermal physics. So this is from 2010, I think. Yeah. So 55th question. The wheel shown in the figure is made up of 3 bimetals. So bimetal, is self-explanatory. Bimetal, P and Q. Strips attached to the axis using radial metal parts. So radial parts are also made up of metals. So this can be set up to oscillate about an axis perpendicular to the plane of wheel and passing through the center. The wheel is designed such that the oscillating period of the wheel remains the same regardless of the changes of the surrounding temperature. Consider the following statements. So just think, here they are explaining it as oscillation. What's mean by oscillation? What's the definition for oscillation? Don't be too technical, just tell. Back forth movements.
Back and forth.
Yeah, it's always back and forth. But here, what they mean by oscillating motion is like the rotational motion, I think. So it's my opinion. So here, what they mean by they can't say oscillation because they are like mentioning about the moment of inertia, and also it should be a rotational motion. So just understand this as rotational motion of the particular system. Okay. So now the moment of inertia of the wheel should not change with the temperature. Okay. The A statement, moment of inertia. Okay, moment of inertia of the wheel should not change with the temperature. So now let's try to explain what is the main data that they are giving. The wheel is designed such that oscillating period, the period of rotation of the wheel remains same regardless of the changes of temperature, changes of surrounding temperature of the environment. So oscillating period T is like constant. Okay, it's constant. So what do you think about omega? Omega should also be constant because omega is 2 pi by T. So T is 2 pi by omega, isn't it? 2 pi divided by omega. So for the T to be constant, omega should be constant because this 2 pi is actually a number that's a constant. So omega should be a constant. So you can actually say that omega should be a constant. Okay, it doesn't change with time. So, and also with the temperature here. Okay, this is the temperature. Then the B, the shape of wheel should not change with temperature. Is it possible? Is it possible? There are bimetal strips. You people know about bimetallic strips, no? Used in iron boxes, and I only know iron boxes. Yeah, iron boxes.
We learn during O levels bimetallic strips. One has a higher heat AC and one has lower.
these are like two strips joined together, okay, very firmly, like attached to each other, okay, and they have different linear expansivities. So when their one end, one terminal is attached and fixed, you can actually predict the movement of the bimetal strips with increasing temperature. So I will give you an example. So this has the linear expansivity of alpha A. This has linear expansivity of alpha B. If alpha A is greater than alpha B, what can you tell about their movement when the temperature increases? Upwards or downwards? I mean, this is fixed. This is attached. Downwards, yeah. This terminal will be like bending towards the downwards, bending downwards direction. So you can actually see the distortion of shape. No? If it's a bimetallistic, there is a distortion of shape. And these radial parts are also made up of metals. So it's also going to like expand. So expansion always occurs outwards. Okay. So this radial parts will push the bimetal parts away from the center. Okay. Away from the center. Is it understandable? Because this is fixed. So when these strips expand outwards, so they are going to push the bimetal parts away from the center. Okay. So is it possible to maintain the shape when expansion occurs? It's not. No. It is not. The shape should change. It's inevitable because when expansion occurs, the shape should change. There will be a distortion. Okay. So we can't take the second statement as correct. If there is expansion, the shape should change. Now C, linear expansivities of metal P should be greater than that of Q. Okay, so now they are actually comparing the linear expansivities straight away. So before that, let's analyze the first two statements. In the first statement, they are saying about the moment of inertia. Okay, so moment of inertia. So now I said that the omega should be constant. Okay, so now think about I omega. What is I omega? The multiplication of I with omega. How do you call that?
Angular momentum.
Angular momentum. Angular momentum is constant provided that there is no torque. Okay, if there is no torque, the angular momentum remains constant. It's conserved. Okay, so now if omega is a constant, the I should be a constant. I should be a constant because the angular momentum cannot change. Okay, I should be constant. So the first statement is actually correct. The I should be constant. Okay, the first statement. I actually didn't explain I. No, I explained up to this point and then I forgot about I. Sorry, I should be constant. Why? T is a constant, omega is a constant. So I cannot change because angular momentum should be conserved. Okay, angular momentum should be like constant. So what are the factors that affect I? I is directly proportional to something and another thing. What are those two things? Directly proportional to the mass, okay, mass, and directly proportional to the square of the distance. I mean, this indicates the mass. This is for the distribution of the mass. No? This is the distance of that point mass from the axis of rotation. So here, this is the axis of rotation. So I said that due to the expansion, the bimetal strips are going to move outwards, like away from the center. So there is a change in R. So you can argue that I is going to change. But I is constant because of these conclusions. T is constant, omega is constant, I is also constant. So R is going to increase because these bimetal strips are pushed away from the center, isn't it? So is there any chance for R to remain for I to remain constant despite this R increases? Like these metal strips are expanding. Huh? Is there any possibility? So they are moved away from the center. There is a possibility for the masses to move towards the center also. How? If the bimetallic strips can bend like this, please unmute your mics. If they can like bend like this, there is a possibility for the bimetal strips to move towards the center. So the change that is created by these metal strips can be actually like neutralized by the bending of these bimetal strips. Okay, can you understand? So what can you tell about the linear expansivities of P and Q? So this is P is inwards and Q is outwards, outside. So what can you tell? Alpha P and alpha Q. So it should bend inwards. Huh? Alpha Q should be greater than alpha P. Okay. What are they telling here? Linear expansivity of metal P should be greater than that of metal Q. P. So if P is greater, what will happen? So it will bend like outwards, no? So outwards. So again, if that condition is true, the bimetal strips are going to move outwards. And also they are moved outwards due to the expansion of the radial metallic strips also. So as as a consequence of those two separate changes, the R is going to increase. So I should also increase. So that cannot be true. Okay, can you understand? Do you have any doubts? You can ask. So here, what are the correct statements? The first one is correct. The moment of inertia cannot change, should not change. So A is correct. The B is false because when there is expansion, the shape will be distorted or somewhat changed. So B is wrong. And C is the expansivity. So that's also wrong. It should be the other way. So A is correct. So A only is true. Okay. Now this is an interesting question from 2013 paper. 2013. Did I give any question from 2011 or 12? No. So 13. A box which is placed on a rough horizontal surface of a table is pulled by a variable horizontal force of magnitude F. For a given value of F, the resultant force R exerted by the surface of the box makes an angle theta with the horizontal direction as shown in the figure. The variation of theta with F is best represented by. So it's a graph question. So let's analyze. So let's first understand how that particular angle is. Like particular force R is generated. Okay, and then only we can talk about the angle. So, if someone says that the surface is rough, so this is this particular thing. This box is placed on a rough surface. So what does that mean by, what is meant by being rough? If we zoom it, what can you see? So now I'm writing on this whiteboard, no? So it is seemingly smooth. But if I analyze microscopically, there will be like elevation, depressions, there will be unevenness. So when you zoom it, you will see that those, in Tamil we say that unevenness, that roughness. And also on this surface, you have that. Okay. So if someone pulls, okay, if someone pulls this box, what's going to happen? These elevations and depressions are going to collide with one another. So for example, this one, you can't, I don't think that you can very accurately see this. So now one is like this and another one is like this. So if you pull it towards this direction, it's going to come and collide with this elevation. This particular depression is going to like, I mean, this protrusion, no? It's going to collide with this particular part of the depression here on the surface. So due to that, there will be a force like this. So on each and every part of the metal, there are forces. There are forces in different directions. So we can express these forces like this. Okay, like this. The resultant of all the reactions due to the collision of these elevations and depressions is this. The resultant is this. Okay, so it has two components. One is actually what is this? This is called normal reaction. Okay, this is called friction, and this is called resultant reaction. Okay, this is resultant reaction. This is normal reaction. Normal reaction is perpendicular to the surface. Resultant is not like that. Resultant is actually resultant of these two, I mean F and the perpendicular reaction. So you can actually determine the direction of R using these two forces. Okay, I will depict them as if they are two adjacent sides of a parallelogram, actually rectangle. So this is F and this is N. So how can you actually find the resultant? By completing this parallelogram. Yeah.
The diagonal.
The diagonal. Yes, that is the first parallelogram. Low. The vector parallelogram. Low. So this is R. So now the angle that R makes with the horizontal plane is theta. So how can you like express this theta in equation? Huh? It's tan theta, no? It's tan theta. So tan theta opposite is equal to opposite side N over the adjacent side F. Okay. So now you can actually talk about the variation of theta with F. F is the force applied. So which component of this equation is going to be affected by this F?
The frictional force.
Yeah, the frictional force. This is static friction. The static, you know the behavior of static friction? No, it is like if you give a force, I will also give a force to maintain the balance. So it's always that relative motion. Okay. So initially, before the motion starts, if it is at rest, the friction, static friction changes, like it's equal to the force applied. Okay. It's equal to the force applied. So then it reaches a maximum point. How do you call that? Special name for that friction?
Limiting friction.
Limiting friction. Yeah. After that, there is a fall, and then you see what friction here?
Dynamic.
Yeah, dynamic friction. Okay, dynamic friction. So that's how you explain the behavior of this friction. So up to this point, this is called static friction. Static friction doesn't have an exact value. It changes according to the force applied. But dynamic friction can be expressed in equation. Okay, so that is actually mu R. And also you have one equation for this limiting friction, only that point. Okay, that's also mu R, and here you should put the coefficient of the static friction, and here you put the dynamic or kinetic one. Okay, so now this is the behavior. So let's analyze what's going to happen if you increase the F. This F is going to increase. So if the F increases, what's going to happen? This ratio will decrease, no? Decrease. So now you can predict the variation of tan theta. So tan theta is going to decrease. So what will happen to theta? Because the question is about theta.
Decrease.
Yeah, you know the tan graph, no? So for acute angles up to 90 degree, you have this kind of a variation. So the tan theta increases with theta. So if the tan theta is going to decrease, theta will also fall, no? It will decrease. And it's the graph cannot be linear. Now you can actually see that because this ratio will not change linearly with f, and also this particular theta tan theta graph is not linear. So it can be, sorry, it cannot be linear. Okay, but it will like decrease like this. So we are not sure about the shape, either this one or this one. This one is not seen in the answers, and this one is seen. So if you are going to like analyze these two shapes, and that's going to be very difficult, okay, for it's very unpredictable because this equation, this ratio, like if you divide something by something, if the denominator is going to increase, it's very difficult to predict the, the value of the fraction. Okay, so now there should be a point where this f falls. What's that point? After the immediately after the limiting friction, the shift point from the dynamic to, sorry, from the static to dynamic. So at that point the f falls, no? So what will happen to this equation? Suddenly there is a fall in f. Suddenly at that point the ratio will show a rise. Yeah, it increases. So what will happen to tan theta and theta? There will be the increase. Okay, so there will be an increase. And after that, the f is going to remain constant despite this f. Why? Because it has started moving. So it's dynamic friction. Dynamic friction is only determined by mu and r, not by the force applied or the surface area exposed, I mean surface area of contact, or any other velocity, or nothing affects the dynamic friction. So it will remain constant like this. So the answer is which one? Answer is the second answer. Okay. 50th question. 50th question from 2013 paper. So a body of mass 2m shown in the figure is placed on a smooth horizontal surface. A small block of mass m is placed at the top of the body, and starting from rest. Block B slides down the smooth surface of A at a constant at the instant when the block B leaves A, the speed of u of A is given by. Okay, this is a very yeah. This is the first time the 11 students had to deal with in this question. Before in the past papers, you cannot see such a question. Here we have to deal with a moving inclined plane. No, it's like an inclined plane, but with a weird shape. No? So like this. It's not like the angle of the angle is not a constant. Okay. So now it's at this point it's like almost horizontal. So the question is when it leaves. So here it has only a horizontal velocity. Okay, so we don't know. That's the question. And this is 2m, and this is m dimensions. So it starts from here. So see there they have like label something as h. So what is h? What is h? The vertical distance between the initial state of the center of gravity Hello? Hello, can you all hear me? Hello?
Yes, sir.
Yes, we
Yes,
have.
sir.
Here we had a power cut. Sorry for that. Okay, so now, so this is the horizontal displacement of the center of gravity. So usually if you don't have a point mass, you talk about the center of gravity. No? So it moves through this vertical distance. Okay. So now how are you going to do? The inclined plane, so this particular object, we can't actually say inclined plane, it's somewhat inclined. So it's going to move because this surface is not rough. Usually we don't see inclined planes moving because we keep them on a rough surface, and that static friction is more than enough to maintain this inclined plane at rest. But here this is very smooth. Okay, so we have to analyze the forces. Okay, first analyze the forces and we can then predict the movement of these two objects. So now I'm going to talk about a very the traditional inclined plane we usually use. Okay, so it's a very, the inclination is a constant here. So if you have a box like this, okay, so this block is placed on this smooth surface. All are smooth, so all surfaces are smooth. So what are the forces? So if you take this block, there is that mg. Okay, what is the only other force? Another force on this block?
Normal reaction.
Normal reaction. Very good. There is no friction here. Normal reaction only. What about the forces on this block? Not block, this one, this object. This one, inclined plane. Obviously, it's mg. Okay, I will put it as capital Mg. And there is also a normal reaction by the flow. So there is R. And any other force? So there should be action which is opposite and equal to this R, no? So that particular force is also there. So this R is there. So any other forces that you can think of? Not exactly, no? Only these. So now, if you can draw a free body diagram for this m, small m, the block. So there is mg. So it has two components, mg cos theta and this theta. Yeah. And there is mg sin theta. Okay, you know all these mathematical things, you know how to make components and all, you know. So I'm just mentioning the magnitudes. So now these are the forces on M, and also you have the normal reaction. So what is the value of this normal reaction? It is equal to mg cos theta. Okay. So now you don't have a resultant force in a direction that is perpendicular to the surface of the inclined plane. So what is the only force now? The resultant force on the small m block. Only force, resultant force, resultant force, only resultant force is this mg sin theta. So it has, yes, mg sin theta. So in that direction, if you use f is equal to ma, so you will get a is equal to g sin theta. And these are like conclusions that you can derive. So you all are familiar with these things. Okay. So this is the resultant force of this block. So what about inclined plane? Inclined plane. So again, I will draw a free body diagram for that inclined plane also. So now you have the capital Mg, you have this R, and you have this R. So I will put it as R dash. So I don't have to erase it. R dash. So now this R is also there. So that R is equal to mg, what mg cos theta. Okay. So now to analyze this, I'm going to take components for this R also in horizontal and also vertical directions. So now what is the value of this component and what's the value of this component? Horizontal one. So you know this is theta and this is also theta, and it's 90 minus theta. What's this?
So can you repeat the question?
Yeah. What is the magnitude of this horizontal component of R? R is already a component of mg, like equal to the component of mg cos theta. And I am going to take components for this R in horizontal and vertical directions. So this is theta. So this should also be theta because those two are corresponding angles. So what's the magnitude of this horizontal component?
mg cos theta sin theta.
Very good. Mg cos theta sin theta. So this is 90 minus theta. So mg cos theta sin theta. What about the vertical component? Mg?
Sin theta cos.
No, this is already cos
Sin
theta. Again, you are going
Cos
to like
theta
take
sin.
cos component for mg cos theta. So it's cos theta cos theta. Okay. This is very weird. Like you can put it like cos square theta, but I'm just putting it like this. Okay, to show it that it's component of mg cos theta. Okay. So now what is the value of r dash here? R dash. Does this inclined plane has a vertical resultant force? Not exactly, no, it doesn't. It is not accelerating in the vertical direction, no. So it cannot have. So this R dash should be equal to the mg plus mg cos theta cos theta. So those are the two downward vertical forces. So that should be equal to R dash, so that you don't have any resultant force in the vertical direction and you don't see any movement in the vertical direction or acceleration. Am I clear? So this is okay. So what is the resultant force on this particular inclined plane? Resultant. These are balanced. What's the remaining one? Mg
mg cos theta
cos
sin.
theta sin theta. So it's going to accelerate in this horizontal direction. Okay, and our block is like accelerating in this direction. Okay, so you cannot actually omit the exclude the movement of this inclined plane. Okay, it will move. Okay, so when this block leaves the inclined plane, this 2m and m will have two different velocities. Okay, so now I'm going to ask you a question. Can you use the conservation of momentum in any direction for this system as a system? Yeah. Now, now, what is the only resultant force on this block? That is in this direction, mg sin theta, no? Mg sin theta. Okay. Now I am going to take components for this mg sin theta also in horizontal and vertical directions. Okay. So what is the value of this one? I will give you angles. Okay, angles. So this is theta, and yeah, this is like, what is this one? This is also theta, no? So this is 90 minus theta, and this is also theta. Okay. So this is theta, and this is 90 minus theta. So what is this component? Mg sin
Mg
theta,
sin theta cos theta.
mg sin theta cos theta. What is this component? Mg,
mg cos square theta.
the sine
The
square.
sine square theta.
Sine square theta. So now you see, here there is mg cos sine theta cos theta, and here is also mg sine theta cos theta. Aren't they like opposite? Aren't they like action and reaction? They are like that, no? Say equal in magnitude and opposite in direction. So they are like action and reaction. So when you take the system as a whole, there is no system as a whole. Okay, when you take the system as a whole, there is no resultant force in the horizontal direction, so that you can use the conservation of momentum in the horizontal direction. Are you all clear? So this is also mg sin theta cos theta. This is also mg sin theta cos theta, so that there is no resultant force for the system. So now you have to think about the system, not separate diagrams. As a system, there is no resultant force in the horizontal direction, so you can use the horizontal, conservation of the momentum in horizontal directions. Okay, so now it's understandable why the diagram is like this. Why? Because when it leaves, its velocity is purely horizontal. So if you have a diagram like this, you can't actually say that, no? It has only a horizontal component. The velocity is not purely horizontal, but here, due to the shape, the velocity is purely horizontal. So that is the purpose of giving a weird inclined plane like this. Okay, so now you can actually use the conservation of momentum here. So that's the reason you have to understand the physics there. So if it is like v, the magnitude is v, now you can just tell the velocity of this 2m. What's that? This is m, 2m, and this is v. Momentum is conserved, so this should be
Half V.
yeah, half v. Yeah, you don't have 20 equations. So now this is how you apply the conservation of momentum, that concept, the momentum concept. So that is not enough to find the answer. But what else is needed? You have to think about how they got these kinetic energies. So that is from this potential energy. Okay, so initial potential energy is equal to the final kinetic energy, because if you take this level as h is equal to 0, okay, this is the 0 level potential energy, so this should be mgh, isn't it? So mgh is equal to the final kinetic energy, sum of those two final kinetic energies, 2m v by 2 square for this plane, plus half m into v square for this block. So now if you solve this, what is the answer for b? They are asking about the velocity of the a, no? Velocity of a. So this one, they are asking about b by 2. So I could have put v and 2v, no? Shall I put like that? So if it is v, this is 2v. Okay, so this should be v and this should be 2v squared. So if you solve this, what do you get? You can cut it. And this is actually 4, so 2v squared. So you get 3, so you can cut the m's, and then gh by 3 within square root g by 3. Okay, am I correct? Yes, the answer is fourth one. So now you understand the physics. Now shall I make some statements to confuse you so that you can try answer? So first statement, okay? So first statement. So there is no first statement, okay? The resultant force acting on this system in horizontal direction is 0. Is it correct? System, horizontal direction.
Yes.
It's
Yes.
correct. The acceleration of the center of gravity of this system or center of mass of this system is vertically downwards.
False.
I will repeat it again. The acceleration of the center of gravity of this system is downwards, vertically downwards.
Correct.
Why do you think so?
False.
Why do you think so? That is correct because mg sin theta and mg sin theta cos theta and mg sin theta cos theta are going to cancel when you consider the system as a whole. So one and only remaining force is this. Okay, so in this direction, the center of gravity of the system will accelerate. Okay, this is the only resultant force on the system. Okay, so that kind of a statement is correct. So this theory is in the objective physics books. I know most of the English medium students are using objective physics because you can understand. So just go through. I don't remember the chapter. Maybe that the chapter is obvious. Law of conservation of momentum. But I'm not sure about the pages and all. I didn't check. But this theory is there. Okay. Okay. In a statement, there is a kind of question called statement questions for ABCD. So in that category, it's there. Okay. So you have to understand why you use the conservation of momentum in horizontal direction and why should this inclined plane move, because it's smooth, so there is no resultant, there is no force, frictional force from the ground. So the only resultant force on this inclined plane is this, so it should accelerate. Okay, so we have spent a lot of time here. So let's move on to the next
Excuse me,
question.
sir.
Yes, you can ask.
Sir, can you please say how it can GH over 3 like that? Can't it be GH over 3? So GH
What?
over 2. How did you get GH over 3? That part.
So this is 2v square. This is all v square. So when you add, it is 3v square. So 3 is going here. Okay, when it comes to the opposite side, it divides.
2v squared means it will come as 4v squared, no? 2 squared?
No, I actually cut this 2. I divide this 4v squared by 2. And this 2m, the 2 it was divided by this 2. I cut here. Okay. So if you just write the equation, if you solve, you will understand. When you see this, you have no idea about how I did that. But when you actually write the equation and solve, it's very easy. Okay.
Sir, conservation of energy is for that M body, no? That
No,
box,
both
no?
M for the system. So this moves through a vertical height of h no. So this mgh is that kinetic energy is given to this block and also to this inclined plane. Okay.
Okay.
So they will divide the energy between themselves. Okay, these two. So now question on electromagnetic induction. It's a very interesting question. Okay. So usually they make the question look huge and you are confused, but no need for that. Okay. So so in summary, what you need to see in this question is one piece of one metal bar. Okay, but it is attached to a Ferris wheel and there are trees and people there. So that's how they confuse you. Okay, so now a Ferris wheel which consists of 2 parallel large wooden wheels joined together with metal crossbars as shown in the figure is erected so that the plane of wheels are in northern south direction. Okay, so in that plane, north south direction. So and the crossbars are perpendicular to the direction of the Earth's magnetic field, which is horizontal at this magnetic field B, which is horizontal at this location. The Ferris wheel rotates around the horizontal axis, passing through the centers of 2 wheels at a constant period of rotation t in the direction shown. LM is a metal crossbar which is at the highest position as shown when time t is equal to 0. Variation of the induced electromotive force at the end L of the crossbar, which is with respect to the end M. So that should be underlined. Okay. So they are asking about the electromotive force at L, okay, at L with respect to the end M with the time t is best represented by. Okay. So now let's study the theory here. Okay. So now when you move a metallic bar like this with a velocity v through this magnetic field. Okay, this is a even magnetic field. Okay, the B is constant everywhere. Okay, so what can you tell about the electromotive force induced here? What's the magnitude? E is equal to, the length is L. Huh? B L B, isn't it? Okay, and also you can also find the direction of that E, the electromotive force. So what's the direction? You have to use your right hand. Okay, in the exams you may be using left hand. Be careful. Okay, you have to use the right hand. Okay, this is my right hand. Make sure that, because I have used like that at the exam time, it's very unpredictable. Do the question. So now this is movement, this is field, and this is the electromotive force. So now inwards field, and in this direction movement, the electromotive force is like this. Okay, so now the direction of E is like this. So you should imagine as if it has been connected to a cell like this. So if it is E, this is also E is equal to BLB. So this kind of a situation is like identical to this kind of a situation. Okay, so now you can tell that in relation to this terminal has a voltage of E is equal to BLB. Okay, so if you talk like this, I mean, if you talk about the voltage of this terminal in relation to this one, what would it be? Minus. Okay, it would be in minus. Okay, it would be in minus. So that's how you explain. And now they are talking about the Earth's magnetic field. You all know that there is a north pole and a south pole to Earth, and there is an imaginary. It's not imaginary. It's really existing. Okay, there is like an imaginary bar magnet inside our Earth due to the different components in the Earth's, the mental and all. So it's like this. It's going like this. It starts from N set S. Okay, South Pole. So if you have a person here, he will only see the horizontal part of it. So now also they are talking about the horizontal component of the Earth's magnetic field. So that is perpendicular to the bars. Okay. So now there is a bar. I can't actually draw that like this, but I can draw the roughly up. So it's like this. So these are moving like this. Okay. So when they move, there is magnetic field like this. So they will like move perpendicular to the magnetic field, or sometimes they have perpendicular component, or sometimes they move perpendicular to the, exactly perpendicular to the direction of the Earth's magnetic field. Okay, so this diagram given in the question is better than my diagram. Okay, you can see that LM is like this, and the magnetic field line is striking it like this. Okay, so it's in a perpendicular direction. So what do you think about the movement of this LM, this bar? At the uppermost part, it goes to the uppermost part. This, if you see the side view, the LM is now here. The magnetic field is also like here, like this. Okay, so now LM is here. So it's going to like rotate like this. So what can you say about the movement? The movement, is it perpendicular to the direction? Movement. Huh? The tangential velocity is like along the direction of this B, magnetic field line. So it's not actually like perpendicular like this. But when it comes here, it will have a velocity like this. And this particular velocity has a vertical component, which actually cuts the magnetic field line. So here, this is exactly perpendicular to the magnetic field line. Here, it has a component. Here, doesn't have a component because it's like this, anti-parallel to the direction of B. Am I clear? So you can actually apply this equation BLB, provided that you have included the sine theta also. Why? Because it's not always vertical, sorry, always perpendicular. Okay. So sine theta should be there. So what is theta here? Huh? What is theta? What is theta? The angle made by the velocity with the horizontal direction. So the component of velocity which is perpendicular to the B is V sine theta. You have to explain this very slowly, otherwise you don't understand. So you have to imagine, connect this diagram with this diagram. This is a side view. This is a three-dimensional view. This is like looking from the front. Okay, I mean you're like in front of this. You are like looking from here. So this is looking from here. This view. Okay. So at this point, you have the maximum electromotive force because it is exactly perpendicular. Okay, so the sine theta becomes 1. Okay, so that's all. Now you can just draw a graph for the variation of E. And what do you think about the polarity here? Polarity means in relation to L, the L's polarity in relation to the N. So what do you think? What do you think about the direction? Huh? It's very boring. I mean, we have to explain slowly, okay? Otherwise you are confused. Okay, what do you think about the polarity? So think about this situation moving perpendicular. Okay, you are looking from here, the front. I mean, you are in the north side. Okay, so you are looking at this bar. The same bar at this position. Okay, so now you see L and M like this, and you will be seeing the magnetic field lines coming towards you. Okay, like this. So it's like this. And this particular bar at that position is having a velocity in this direction, exactly perpendicular to the direction of B magnetic field lines. Okay, so now I'm going to use that rule. So it's comes towards this and this. So what do you think? Keep your hands like, okay, place it along the correct directions. Okay, the movement is like this and the field lines towards, okay, like this. Okay, it's very difficult for me. So now you can find the direction of E. That's in the direction, in this direction. So, which is in higher voltage, which has the highest voltage, L or M?
M.
L, no? L. So it's like this. The cell is connected like this. It's similar to this. So L has higher voltage when compared to M. So when it moves like this, the graph should come in the positive direction for this half and the negative direction for this half. Because if once you have worked out this part, you can actually automatically, the answer will be in your mind when it is in the opposite direction. Okay. For this half, the L will be having lesser E in relation to M. So it's negative. So the variation should be like sine, and for the initial half, from here to here, it's in the positive direction, and the next half it's in the negative direction. And here it starts as 0 because the theta is 0, and at this point at 90 degrees, it is maximum because the theta is 90 degrees. No, not this theta, no, this theta. 90 degrees, so sin theta is 1. Otherwise, that's all. Those are enough to find the answer. Are you all clear about this? Huh?
Yes.
Okay. If you have doubts, you can ask. So next question. It's actually a very interesting question. Okay, 2015. So you should be able to predict. I mean, it's not logically predict the variation of capacitance. Okay, variation of capacitance, the voltage difference between the two plates, the electrical potential energy, what else? E, okay, electric field strength between the plates of the capacitor when
Excuse me, sir.
yeah, then
So you missed 31st question of 2014.
31st question of 2014. 31st. Did I get? I missed it. Okay. So can you read, please? I will be able to explain. Can you read, please?
3 different types of thermometers P, Q, and R having a temperature range of 0 to 110 degrees Celsius and kept at room temperature of 30 degrees Celsius were simultaneously dipped into a large oil bath maintained at 100 degrees Celsius at time t is equal to 0. And their readings were theta recorded with time t. Curves in figure show the variation of theta with t for 3 thermometers. Consider the following conclusions made about the thermometers after analyzing the 3 curves.
Okay. Okay. Before reading the statements, let's analyze the graphs. Okay. So they are simultaneously. Huh? Simultaneously. So they are simultaneously placed into a container. So this is 100 degrees Celsius. The temperature of the oil is 100 degrees Celsius. So this is time. Okay. So you should first try to interpret those graphs. Okay. There are some conclusions that you can make. So this is with time. Always remember, okay, this is with time. The variation of temperature with time. So which thermometer is quicker?
P.
P is quicker. Which thermometers are correct? Accurate.
P and R.
P and R, not Q, because Q is showing somewhat a reduced temperature, not the exact temperature of that oil. So So those are some conclusions that you can take. The fastest is P, and other two are slower, and Q is not accurate. P and R are accurate. So when it comes to the thermometers, if I explain the theory to you all, yeah, when it comes to the thermometer, you need to think about you should know mainly four things. One is sensitivity, then accuracy, then what's the other thing? Responsiveness. Okay, responsiveness and the range. So what is sensitivity? Sensitivity is, listen to me carefully. Sensitivity is about how much the thermometric property changes with the temperature. How much? Okay. So if it is like showing overreaction, like some people, when there is a small change, the reaction is very high, very big. Yeah. If that thing is there, that refers to sensitivity. So you can actually define it as the change of thermometric property per unit temperature. Okay. Or per unit temperature. Okay. So delta X over delta theta. We can express this like this. Accuracy is about how correctly it reads the temperature. Responsiveness is about, can you tell me what's responsiveness? How? It's about how?
How fast?
Yeah, how fast it responds. Okay, how quickly it responds. And range is about
minimum and the
minimum and
temperature.
maximum temperatures that can be measured using the thermometer. So range is actually determined by the thermometric substance, its melting point and boiling point. Okay, and also how the thermometer is made. For example, you can measure up to 386 degrees Celsius using a mercury thermometer, but that is manufactured in order to measure only from 0 to 100. So then that factor limits. Okay, the manufacturing process limits the range. So the ultimate factors limiting the range are the melting point and the boiling point, but it is also dependent on how the thermometer is manufactured. So sensitivity, accuracy, responsiveness. Can you tell anything about sensitivity using this graph? Huh? No, you can't tell anything because it's not about the temperature and the thermometric property. This is about how fast. Okay, this is about time and the temperature. So what actually determines the sensitivity when it comes to the mercury thermometers or liquid thermometers? Yeah.
The way the scales are arranged.
Not scales exactly. The property of thermometer. Yeah. You
The,
have that
the
expansive.
heat testing of mercury.
What heat? What heat capacity?
How? Yes.
No. You should be very clear about this, students. Okay, I will explain. Okay, this delta V is equal to V naught gamma theta, the expansion of volume. This is a volume increase. So this increased volume is like pushed into the capillary tube. So if you divide the volume change by cross-sectional area, both sides, okay? Both sides, if you divide it like this, you will get the change of length. What you observe is length, not the volume. Okay, in the capillary tube, you are observing the length. So V naught gamma theta over pi r square. So I am putting this A as pi r square because usually what we compare is the radius of the capillary tube, no? So to increase the change of the thermometric property, which is change of length, you should decrease the radius and you should increase the volume of the mercury. Okay, so that is those are the factors that affects. And if you can get a liquid with high expansivity, that's also going to contribute. Okay, so you're always taking usually alcohol or mercury, no? So that factor doesn't change very much practically. So we actually can change V naught and R. Those are the manipulatable factors. What about accuracy? Accuracy is about how correctly. Okay. So what happens is usually if you place a thermometer inside a liquid, okay, the liquid should give some amount of heat to this thermometer for the mercury and the glass to somewhat expand. No? So that amount of heat is sometimes significant. So when they give significant amount of heat to this thermometer, the temperature of this liquid falls. Okay, so that you actually kept the temperature at 100 degrees Celsius initially, but now it has fallen to 99 degrees Celsius. So what is the reading here? 99 degrees Celsius. Okay, so it's not correct. It should read 100 degrees Celsius, but as it has absorbed significant amount of heat from this liquid, now it's showing 99 degrees Celsius. So he is not accurate. So what factor determines the accuracy? That is the amount of heat absorbed from the system by the thermometer. So the factor that determines the accuracy is the heat capacity of the thermometer. Okay, so if the thermometer mercury and the glass has a high effective heat capacities, they need higher heat to expand. Okay, so you should reduce the heat capacity. So what should you do? You have to reduce the amount of mercury you use. So mass of mercury or volume of mercury, volume of that bulb should be reduced. And also you have to reduce the thickness of the glass used. Otherwise, if the thickness is high, the amount of substance of glass is also high, so the mass is high. So you should reduce the thickness. You should reduce the amount of glass used. So you reduce the thickness. You can't reduce the surface area, and surface area is needed. So you have to reduce the thickness to somewhat reduce this C. Okay, so that a little amount of heat is absorbed from the system. So these are factors affecting the accuracy. Yes.
Should we reduce the whole thickness of the whole thermometer or only that capillary part where the mercury is there?
Mercury is inside the bubble. Sorry, not bulb. Sorry, bulb. Inside the bulb. We have to reduce the thickness of the bulb. Okay. I was meaning the wall thickness of bulb.
Okay.
I didn't mention that, no? Wall thickness of bulb. So when you immerse the thermometer, I'm exaggerating the bubble. Sorry, bulb. Okay. So it has mercury here. So the wall of the bulb will have a thickness, no? So first this particular part of the thermometer will absorb heat, and then it will go to what? The mercury. So the amount of heat is determined by the thickness also, because if the thickness is high, the amount of the glass is also high. So you have to give some amount of heat to this and some amount of heat to this. So if they are high, the absorption of heat becomes significant, and that significantly reduces the temperature of the liquid. Okay. So what about responsiveness? Responsiveness is about how fast. Okay. So that is also determined by the wall thickness. Okay, if the thickness is if the wall is very thin, the heat travels faster because the rate of flow of heat is Ka into theta 1 minus theta 2 or delta theta by L. No? So if you reduce the thickness, the L is reduced, the rate of flow of heat is increased. Okay, you understand? Usually you don't change the A. Okay, A is not much change because A is needed. Okay, A is like fixed because that is determined by the volume of this bulb, but the thickness is like changeable. Okay, so you reduce the thickness as much as possible so that when the temperature of the liquid or the substance that is the temperature is being measured, if the temperature changes suddenly, the change is transferred to the mercury very quickly when you have a very thin wall. Okay, you understand? So the responsiveness is determined by the thickness of the wall and also the amount of mercury used. Okay, so if you use a higher amount of mercury, so the mercury as a whole should get heated to that particular temperature. No? So it takes time if you have more mercury. The range I have already told you. So now let's go to the statements. Can you read that? I don't have past paper, I left it in Colombo. Can you read this? Please, someone read the statements.
Statement A. P is the most sensitive thermometer.
Yeah. Can you tell anything about the sensitivity here? Not exactly. No. You need the graph, the L versus theta to compare the sensitivities, the length and the theta graph. So one is like this, one is like this. This is A, this is B, which has higher sensitivity.
A.
A has high sensitivity. Yeah, you can't tell anything about sensitivity here using this graph. But the next statement was the next statement.
Thermometers P and R are accurate but not Q.
Yeah, that is correct. Okay, Q is not accurate. The next statement.
The scale of thermometer R is not linear.
Thermometer R is not linear. We can't say that without seeing the calibration. No, I mean we have to see that. This is about with the time. Okay, with the time. So you can still have a evenly calibrated that scale. Okay, so this is about how the temperature reading changes with the time. So maybe the liquid that is used here doesn't expand like, I think the linear expansion varies with the temperature here. Okay, but somehow it finally comes to this temperature. So it's with the time. Okay, with the time. It unevenly expands with the time, but it can expand evenly with temperature. Okay, so for these two, for example, I have drawn the graphs for length, width, temperature. So if it is linear, the calibration will be linear. If it is like curved, not linear, the calibration is going to be the scale will not be linear, no? Because for example, if you take 5 degrees and 10 degrees here, so length is not actually twice the length corresponding to 10 degrees Celsius is not actually twice the length for 5 degrees Celsius, no? Due to the shape. So this particular thermometer scale cannot be even. Okay, it will have different intervals between the temperature. Okay, the temperature values. Okay, am I clear? Huh? Did you understand?
Yes, sir.
Okay, next question. Yeah, 2015. We only have 3 or 4 more, 5 more. Okay, we can quickly discuss it. So you should be able to work out logically how the parameters of a capacitor changes when you insert a dielectric substance. So this particular question is about that. So an air-filled parallel plate capacitor of plate separation B is fully charged using a battery of voltage V0. When the battery is removed, okay, it's removed, and the space between the plates of capacitor is filled with a material of dielectric constant K. If the energy stored in the capacitor when it is filled with air is U0, and electric field intensity across the capacitor, the energy stored in the capacitor when it is filled with the dielectric material E and U are respectively. So now you have to compare the electric field strength and the electric energy stored. Okay, that's called electric potential energy of a capacitor. So let's analyze. So this is like after the voltage source is removed. So now it is called, how do you call this kind of systems? Huh? How do you call? It is removed, okay? It's removed, but it's now charged. Already it's charged. But now they have, sorry. Now they have removed the voltage source, but still the charge remains. Okay? Thanks. So you can also explain the same, you can also explain the same scenario when the capacitor remains connected to the voltage source. So I'm going to explain both because in the future the question can be changed. So you will be able to answer this kind of a question also. Okay, now I am inserting a trielectric substance. Okay, it's now filled, totally filled, okay, completely. So what do you think about the capacitance? So the initial capacitance was C, okay. Initial parameters are like just letters C, okay, U, okay, they are giving like U naught, but I'm just writing U, E, okay, what other things? Q, V. So all these things should be short. So now let's discuss what happens to C. What happens to C? C will increase or decrease? Huh? Are you all there? 48 students. I'm so happy about this. I mean, this is the first time I'm teaching English medium students, and the students are in the class with patience. Okay, good. Good to see this. So C is actually how do you so you can prove an equation for C, okay? So what's the final equation? Epsilon naught A over D. So what is this epsilon naught? Can you define that? Not define, just tell what is meant by epsilon naught. What? Electric field. What is meant by this is permittivity, no? There are several types of permittivities, and this is electric. Okay. So it is in the free space. Free space means vacuum or air. Air is like almost equal to the permittivity of a vacuum. Okay. So usually it's like this. Now you have inserted this dielectric substance. So what is the new C? C final. Huh? Tell, quick. This now the dielectric constant is K. So it's not epsilon naught anymore. It's K epsilon naught A over D. Am I correct? K epsilon A over D. So when you express this equation in terms of initial C, it is then Kc. So the capacitance increases by the factor K when you insert a dielectric substance. So what's going to happen to Q? Q final. Tell, this is an easier question. Huh? Will it change? Huh? It is not connected to any voltage source, no? So it is like separated from the external environment. So the Q final is also Q. So there is no chance for these charges to escape. So the Q remains Q final remains Q. Okay. Then what about V? You know the equation Q is equal to CV. So Q is a constant. So when you increase C is increased. So what's going to happen to V? Huh?
Decrease.
Should decrease. By which factor? By the factor K again, because it increases by K. It increases by K times, so it should decrease by V again K times. So new Vf is V by K. Am I correct? Okay. So what do you think about U? the energy stored. There are three equations for U. What are those equations? U is equal to half VQ. So you are having a capacitor being charged. So if you graphically, if you graphically give the change of Q and V in a graph, okay, so it will be like this. So the area of this below the graph is equal to the energy stored, so it's half VQ. So when you substitute Q is equal to CV here, it becomes half CV square. So when you substitute V is equal to Q over C, it becomes half Q squared over C. So you can use any of these equations, not any of these, the suitable equations from these three, out of these three, to compare U. So what is the most appropriate equation? So this equation is also okay. This is also okay because Q is constant. So using the other factor, you can actually predict the change of U. So the Q is constant, isn't it? The Q is constant. What happens to V? V decreases. So U should decrease. Or you can come to this equation also. The Q remains constant, C increases. As it is the denominator, the U will decrease. Okay, so U will decrease by the factor K. Okay, so again, the U final is K times smaller than the U initial. Okay, what about E? E, what do you think about E? Huh? Do you have any equation for electric field strength? Huh? So it is V over D. V over D. V is the potential difference between these two plates. The D is the separation between these two plates. So now the D is not changed. The V is like reduced. So E will decrease. So it's also by K times. Okay. Now answer this question. So in this question, the capacitor remains connected to the voltage source, and now it is completely filled with a dielectric substance. So what's going to happen to C? What's going to happen to Q? What's going to happen to V? What about U and E? So respectively, can someone tell increase, decrease? Like that? Huh? Can you answer, students, please? Milshi Fernando, can you answer? What will happen to these things? So again, you can use these equations, okay? So what about C? C is affected by epsilon naught A and D. So A and D are not changed. So epsilon naught is going to increase. So new permittivity is K epsilon naught. So C will invariably increase whenever you put dielectric substance. Okay. So now it is again Kc. By factor K, it increases. What about Q? What do you think about Q? Q is equal to CV. Okay. So now, what do you think about V? Voltage difference. Huh? Tell quickly. Otherwise, we can't finish it on time. Please answer something. So you all are like logged in and doing some other work. Huh?
No, sir.
Yeah.
Decreases.
What about V? V, it remains connected to the voltage source. So here the factor that determines the voltage difference is the source. Okay, now he will maintain the constant voltage difference because he is there now. He is there to look after. So the voltage is going to remain constant. So voltage is constant. C increases, so Q should increase by the factor K again. So it becomes KQ. New Q is KQ. So what about U? Again, you had to use these equations. So what do you think? So V is constant, Q increasing. Huh? So U should increase. No? U should increase by the factor K. So what do you think about E? Using this equation, E is equal to V over D. D is not changing, V is also not changing, so E cannot change. So new E is E. So now actually you can answer this question. What's the answer? Huh? V becomes V over K, U becomes U over K. So what's the answer?
Second answer.
Second one, no? They are not giving E, but they give V over D. So again, if you put K, that's the answer. V over D is E, no? So that's the answer. Good, very good. The next question, it is one of the most difficult question. Okay, the next two questions are considered to be two difficult questions from 2015 paper. The paper itself very difficult. Okay, those two are from hydrostatics. So let's see. So a vessel of uniform rectangular cross section with height h0 and mass m contains a certain amount of oil having a mass m and density rho oil as shown in the figure. The vessel floats vertically in the water of density rho naught greater than rho oil with height h1 underwater. A certain volume of oil is now replaced by an equal volume of water. If the maximum volume of oil that can be replaced while keeping the vessel floating is V. Okay, the maximum volume of oil that can be replaced. So replacing means you are taking a certain volume and you are replacing it with water, the equal volume of water. Okay, so this is if the maximum volume that can be replaced while keeping the vessel is V. So if you put a little bit, if you replace a little bit more than V, it's going to like goes in. Okay, it's going to go inside. It's going to immerse. So the initial volume of oil is V naught. Then the ratio V over V naught is given by assume that the end of the process there is certain amount of oil left in the vessel. So you are like keeping the oil, okay, to some extent. So there is adequate amount of oil initially, so something remains at the end also. Okay, so now how do you deal with these questions? So now I'm going to give you a very simple question so that when you understand that simple question, it will be very easy for you to analyze this question. So now see, there is a block like this, a wooden block. So it floats up to this point when it is put into the water. So this is h, and this the total height is h0. Okay. So now to immerse it like this, there is a force applied here. Okay. So I'm applying a force on top of this wooden block to immerse up to this point. So now I'm asking you the magnitude of this force. Can you work it out? Like this is rho and this is rho w, the densities. What are the things? This is A. So can you tell me the magnitude of it? Huh? What is the magnitude of F?
Rho G.
Rho GH.
It's not
No.
to rho GA.
Very good. Very good. So a good instant answer like that. So you can give an instant answer. How? So let's analyze the let's apply the law of flotation here. So you know, to flow, the U should be equal to the weight mg. Now the U is actually given by U is actually equal to the weight of water or liquid displaced. So this is V rho G. This is W always. Okay. So now W is balanced by this V rho G. So what is V rho G here? So for V we can substitute it as AH. Okay. Cross sectional area into height immersed rho G W. So now you should make this H as H naught. So you should increase the right side of the equation. So you can place some weight, or else you can apply some force. So here we are applying force. So by applying force, what we expect is we have to get this part of the wooden block into water. Okay. So here you can see the A, rho, G are constants. So the H is directly proportional to the weight. Okay. So can you write it like this? The F should bring this part of the wooden block into the water. So what is this part? This is H naught minus H. Okay, H naught minus H. So the H naught minus H is directly proportional to F. Is it wrong? This is correct. The F should bring this part of the wooden block into water. So this particular height is directly proportional to the F. So now you just divide these two. You just divide these two. So H over H naught minus H equal to V over F. Okay, so now you can find it. H naught minus H. Sorry, over H. H into W. Can you substitute something for W? Yeah. Yeah. You can substitute this. So H W over minus H over H into AH rho G. So it's very easy. Okay. HW minus H into A rho G. Okay. So that's how you write direct the proportionate relationships, and then you solve without writing equations. So here, can you apply the same thing? Yeah. Here you are not applying force, you are increasing the weight. Okay, you are increasing the weight. Why? How? You actually replace some amount of oil with water. As the water is denser than the oil, there will be a net increase in the weight of the system. Okay, so now initially the weight of the container is M. Okay, weight of the container is M, plus it has some amount of liquid which is small m in mass. So that is directly proportional to what height? What height? It is H1. It is H1. So now you should immerse H0 minus H1 into water. Okay. So this is proportional to what? What? The increase of mass. So when you remove V volume of oil, there will be a reduction initially in mass, and now you are adding same amount of water. So this is going to be subtracted from the mass of the system, and this is going to be added. So the resultant increase in the mass of system is rho W minus 1. So this is rho W minus 1. Okay. So now just divide. Okay. So this is, so I'm going to divide this by this. Okay. So V into rho W minus rho naught over M plus N equal to H0 minus H1 over H1. Now what they are asking is V over V naught, isn't it? They are asking V over V naught. So V over V naught. So I have to somehow bring this B over B naught thing. Okay. So usually what do? We just divide by B naught in both sides. Okay. So I'm going to divide 1 over B naught here, and I'm going to put 1 over B naught here also. So just make it a subject. B over B naught a subject. We just multiply H naught minus H1 over this comes here. So rho W minus rho naught into H1. But you can't keep it like this. Can you keep it like this? Somebody will come and cancel these two. Then it's gone. You can't keep it like this. So you have to subtract something to this. So this is initial volume of what? This is initial volume of oil.
Oil.
No? Oil. So you know the initial mass of oil, M. So you know the relationship between the mass, volume, and the density. So V naught into rho oil is equal to M. So you're just going to substitute V naught with M over rho naught. Okay, so it's rho oil. So I'm not writing I and L O because I'm lazy to write that. So M over rho oil. Okay, so this is the equation. So can you find a similar equation somewhere? Yeah, it's in the first answer. No? Okay. So what do we do usually is when I was given this question, when I studied so in 2016 batch, I go always in the proportional method, okay, proportionate relationships. And after writing this equation, straight away I mark the answer because not all the equation has these components. See, some has M minus M. Okay, so you can eliminate those answers. Okay, and the only equation that contain this and this without any unnecessary components is the first answer. So I just mark the first answer. Okay, so like that you can do if you don't have time. At that time we were given like an exam to do that within a limited time, and that question I was doing for the first time. So I just put it like that and mark the answer. Okay, so not always you have to find the final answer. So you can just mark 50th question 2015. So it's always a risk to take this question for explanation because sometimes we become confused when we do these kinds of questions. So let's try to be clear. Okay. Let's try to be clear. Okay, I will explain this very slowly using some examples also. So now an object in the shape of a truncated solid sphere. So it's not a complete sphere. Truncated one of radius r is kept at the bottom of the tank as shown in the figure. The distance from the center of sphere to the bottom of the tank is L. The tank is now slowly filled with water. Assume the truncated sphere is fixed to the bottom of the tank so that its bottom surface does not get wet. The variation of the vertical upward force F is exerted. Vertical upward force F exerted on the object by water. Underline that, okay? Vertical upward force exerted on the object by water, not the normal reaction by, not anything by the container. It's by water, okay? With height h of the water is best represented by. So now you have to think. Just telling that it's not wet. Okay, the bottom part does not get wet. Okay, so why is that? Yeah, water is not touching that surface. So water is not like traditional examples that we unlike traditional examples that we study. Water is not going to exert any pressure or force on that particular part that is attached to the container. Okay, so this question is somewhat different. So let's analyze the force exerted by a liquid on a surface. Okay, so I'm going to take this example. That is a cylinder like this, an even one, uniform cylinder. Okay, so it has a surface cross-sectional area of A. And now I'm hanging this from a support, and it is now placed inside a vessel like this. Okay, and now I'm pouring water into this little by little. So now it's filled like this up to this point and filled to this point. And now I have filled up to this point. Okay. So I'm going to label some heights here. So this height is h. Okay. So this is the height of water above the level of the lower the surface of this cylinder above. Okay, only above. So what do you think about the pressure on this surface? Huh? From this level, the height is h. What do you think about the pressure P?
H rho G.
H rho G. That is very simple. No? What do you think about the force by water, due to water?
H rho G over A.
H rho G over A. H rho G over A. So usually for
Into
F
A.
is equal to F
Multiply
of A multiplied by A. H rho G multiplied by H rho G A. Okay. Okay. So now be clear about this. So the force exerted due to a liquid is the multiplication of the pressure and the surface area that we consider. Okay. So like that. So what will happen when you increase the water level? It will anything happen to this F? When you increase H, F will be
Increasing.
increasing. Yeah, F increases directly proportional to H. Okay, so it remains directly proportional to H because the other factors are constant, rho G A. So that's how you have that increase of force with H, and that's how you get force due to the pressure, and those basic things are here. This is a very traditional example. Okay, the bottom part is wet. Okay, it does get wet. What will happen when you attach this to that thing? So I'm changing the diagram. Okay, not a new diagram. I'm just changing the diagram. So what will happen if you attach so that it does not get wet? The lower surface does not get wet. Will there be a force like this?
No, 0.
No, there will not be because the water is not in touch with this. So it's like there will be forces like this. Okay, on these surfaces, those are like cancelled. So there is no resultant force due to water. So it's 0 always, whatever you feel. But when you feel like this, above this point, there will be pressure on this face. No? So that will come. That will create a force downwards. So now let's analyze the pressure. So we have explained the theory. Okay, now I'm going to draw this here. This is the big container. Okay. So today I don't know the reason why I'm drawing pictures. Why I'm drawing pictures at once. Yeah, I didn't erase. Otherwise, I play a lot of mistakes, erase, and I'm very poor in drawing diagrams. But today is like 15. So it's L, and this is R. Okay, so now you are going to like fill water like this, little by little, slowly, and now the H is increasing. So now you are going to analyze what's going to happen to the upward vertical force by water on this sphere with H. Okay, okay. So now after you put some amount of water, the bottom parts, this part of the sphere is going to get wet. No? So it will get some force due to water. So that force, so let's consider this point, the bottommost point. So if it is H, so you can tell that if you consider the force on a small piece of area, delta A, at the bottommost part of this sphere, that's going to be like H rho G into delta A. I'm considering in that small part of the surface, okay? So that's why it's like delta A. So it's H rho G A. So what will happen to this force when you fill on that particular part of the surface? Huh? If you go on increasing the H, what's going to happen?
Increase.
What's increases?
Yeah, it increases. F is directly proportional to H. So on that particular point, the force is going to increase. So you know the direction of force, it's always perpendicular. But we consider when writing the equation of pressure is the perpendicular force. So if you derive an equation for F using the pressure, that is automatically a perpendicular force. Okay, you can understand because you calculate using the perpendicular pressure. So when you calculate, perpendicular force, when you derive the force equation using pressure, that force will be perpendicular to the surface because that's the force that we consider. Okay, so this will be like in this direction. So it has a vertical component and a horizontal component. Okay, so this side is also like that. Okay, I will be just explaining using one side, but this side is also the same. There will be a force like this. So it will also have a vertical component and a horizontal component. You can see the horizontal components are in opposite directions, no? So this horizontal component will be cancelled by the horizontal component on the corresponding surface area. Am I correct? With the same level in the opposite side, the horizontal force is going to cancel this horizontal force
Excuse me, sir.
by its horizontal force. Yeah.
Will the force on both the sides be the same, the magnitude?
We are considering the corresponding sides. Okay. So if you are like taking the bottommost delta A, you are considering the bottommost delta A surface on the opposite side. So you are considering the corresponding sides. You are pairing the opposite surfaces. Okay. So it's going to be same. Do you understand? You consider the corresponding one in the opposite side. Identical one, but the opposite. Okay. So the same force, same H, same rho, same G, same A you are considering. So that the horizontal components are going to cancel. So the vertical component is the resultant. So it's understandable now because they're asking about the vertical force. Okay. So just for theory, we are discussing the horizontal part also. Now it's cancelled. Now I'm going to only discuss about the vertical force. Okay, because that is the only one existing there. So now when you increase the height, the vertical component will be increasing because as a whole the pressures at all the points will be increasing due to the increase of H. So that particular part of the surface area will also show increase in force. No? It will get more force. Okay, when you keep on increasing the H, this force will increase and this vertical component will also increase. So when you draw a graph for that particular surface area, force on that particular surface area with H, what will happen? It will linearly increase with H, no? Because we are considering only that part, small part. For that small part, if you draw like this, you will get this kind of a diagram. So is it the only surface that is available for force to act? No, there are several, there is a plenty of surface. When you increase the height, there are new surfaces that get wet. You understand? New surfaces are like getting wet when you increase this. So the already existing force is increasing linearly with H, and also new forces are generated because new parts are getting wet. So will there be a linear increase or something more than that? Already
More than
existing forces are more than that. Already existing forces are increasing and new forces are like created. up to this point, there will be vertical component for all the forces here. This point is like purely horizontal. So up to this point, there will be vertical components for the forces. So as a result of new forces generated, this is not the change for the total force. There will be a change like this. Acceleration, like, you know, the displacement time curve. For acceleration, it's not like this, no? So like that. Some increase in rate. Okay? Because already existing forces are increasing linearly and new forces are created. So that it is like a curve like this with increasing gradient. Okay? So what will happen after this? After this point? After this point, if you start to fill it up, yeah, new forces are generated again, but those new forces are not like these ones. So their direction is like this. Okay, but their direction is again perpendicular, but they have a horizontal component which is cancelled, and they have a vertical component which is vertically downwards. Okay, so now the newly generated forces are actually cancelling the already existing forces because those are in the opposite direction. Okay, see this children. These are in opposite direction. So this is going to reduce the already existing force. For example, so this part has a corresponding part in this side. Okay, so if we take this level, so I'm taking a point which is above this level, and distance between this point and this point is r, and I'm considering another point which is below this level at a distance of r, and now these two are corresponding, corresponding surfaces, and this has a vertical component for the force, and this has a vertically upward component, and a downward component, and this part, the force on this part will cancel the force on this corresponding part because they are opposite in directions. So the newly generated force after this point are going to cancel the already existing ones. Okay, do you understand? So now, yes.
You said means this surface tension forces also come.
What forces?
Surface tension.
Surface tension. Surface tension here they don't mention about that. So even, I mean, surface tension. We don't usually think about surface tension here. I mean, if you think about surface tension, yeah, it becomes more complicated, isn't it? You can also think about, but we usually don't consider those surface tension forces when we talk about the hydrostatic forces, no? So just forget about it, otherwise it's more confusing, no? So we don't consider actually. It should be mentioned, I think. Okay, it should be mentioned. Surface, ignore the surface tension effects. They could have mentioned. Okay, it's fine. Let's just discuss. Yeah.
So according to this, when the height of the water increases, it will the forces will get cancelled and it won't move. It will stay stationary.
No. It's not. It's increasing because just think, if you increase the height, the pressure at this point, the bottommost point is going to increase, no? So the already wet points increase their force. I mean, when you increase the height, so all the points here will get more pressure. So the more force. But what's going to happen? The force on this part is like linearly increasing, but that is somewhat dampened by, so how to say, it is somewhat opposed by the newly generated downwards forces. So will it be like this or less than this? I will repeat that. Okay. I will repeat
So,
that.
sir,
So
the newly generated downward force will not be equal to the upward force, right? Then
yeah, that upward force is already greater than the
Greater.
downward force now created. You understand? So these areas, the whole area is creating upward force. No, this is all now wet. So when you increase the height after this point, due to the increase in height, the force on this surface is going to increase. Okay, upward force will be increasing. So if it is the only part that we consider, the graph will be like this. But there are newly generated forces, no? So newly generated forces will have a opposing effect. Okay, or we can't say that. That's not correct. Opposing effect. So will it go like this or somewhat below that? Below. After this point, below. Very good. So it will be like this, the resultant graph. So after what point? So this is L, no? So after L, it's going to be like this. Okay. So now just think. So you have now put water up to the L above this plane. Okay, L above this plane. So now there is a surface that is similar to the surface below. So this surface has its enemy here, its opponent. So now those two have corresponding points. I mean, which are against each other. So what will happen when you add more water? What will happen to the forces on this and this half? Not the above one, okay? The L part above and L part below the level of center.
Cancels off.
Yeah, they will cancel each other. Yeah. So now there is no effect. After this point, there is no effect by this part and this part. So now the remaining part, now the game changer is this part. Okay, now this is the main character. Okay, so now when you increase, now the resultant is the force on this part. Okay, so that will have what component? Vertically downwards, upwards.
down.
That is downwards. So downwards, only downwards. So this is cancelling this. So there is nothing due to the surfaces below this level. So now the new forces created are going to create a reducing effect on the already existing force. So now there is an already existing force like this. So now the newly created forces, newly generated ones are reducing it. And that rate is also increasing. Why? Because here also you see newly created up to this level. So this is like, you know, this is L, this is also L, and this is R. So up to this should be 2L, no? This should be 2L. And up to this point, you have R plus L. Up to this point, you have increasing effect. Why? The same newly generated forces are there. But newly getting wet. Okay. So after this point, after this level, if you increase the height, will you have any newly generated forces?
No.
It is totally immersed, like the sphere is totally immersed. So now if you put water, there is only that height effect. The height will increase the already existing forces. Now the already existing force is only this one, because you know this part is cancelling this part, so that the part that is similar to the removed one, okay, here there is a truncation now. So the similar to the removed one, there is a part now which is not removed in the upper part. So that part, the force on that part will increase linearly with h, because there is no new generated forces after totally immersed after this point. So it's going to have a linear graph after that. So you have to observe the graphs, okay, and then find the answer. you will find the fourth and fifth as similar graphs, but there is a small difference. What's that? The fifth one after L plus R, it's not linear. Okay, so you should have a good eyesight because it's really very difficult to differentiate those two. Okay, this one is very similar, but if you see carefully, you will observe there is a linearity only in fourth answer, not in the fifth answer. So what's the answer? It's fourth answer. Okay. Only 2 questions more. Any doubts? Any doubts?
Excuse me, sir.
Yeah.
At the beginning, when we took pressures, we neglected air pressure, no atmospheric pressure. What is the reason for that?
Because it's only the force that is asked here is only the force by what? Water. I told you to underline. Why? Because it's only, they're asking only about the force by water. Okay?
Okay, sir.
Okay. Any other doubts? Any doubts you can ask.
So there was a doubt in the chat box.
What? The chat box, no? Okay, I will check it. There are a lot of. If the object is a uniform sphere, then the horizontal forces will cancel each other. I didn't follow this. There are words. I see only words. I don't. Vessel slanted, they may vary, right? The vessel is slanted. No, even if it is slanted, yeah, I mean, slanted, we are complicating that. I mean, the corresponding parts are not wet. No, it's asymmetrically wet, getting wet. Okay, asymmetrical. So we can't actually, it's very difficult to predict. And I don't think so. According to this question, it depends on the object. Yeah, you're answering the doubt. Okay. If the object is uniform sphere, then the horizontal forces will cancel each other. What do you mean by uniform sphere? This is a truncated one. Okay, it's truncated to prevent, to actually change the question. Otherwise, it will be like a normal question. No, it will be like the answer would be like this. If it is not like truncated, yeah, it's not truncated and attached. If it is like a full sphere, the answer will be like this, and after that, it will not change. I think. Excuse me. Wait. It will be like this. Answer would be like this. If it is a sphere just placed hanging, like I explained the cylinder example. So for this part, you will have this kind of a graph. For this part, you will have this kind of a graph, and then it will not change. Okay. Always the below parts will overwhelm the upper parts because always the depth is higher for the lower part of the sphere. So it's constant and that's the upthrust. Okay, if the object is uniform sphere. Okay, you can ask doubts. Okay, you can just unmute and also ask. Do you have any doubts? So it's not just an upthrust question. So this different question. So that's why it's very difficult to somewhat explain also. Okay, hope that you all understood. So next question is two narrow tubes of equal lengths but different radii of cross section are connected end to end, and water is allowed to flow through it as shown in the figure. So it's a very atypical question. Okay, it has never come in the past papers also. If U1 and U2 are average velocities with which water flows through the cross sections of the tubes, and P1, delta P1 and delta P2 are pressure differences built up across the tubes as shown, then the ratio delta P1 over delta P2 is equal to. So now they are relating the velocity with the pressure difference. So usually we study the rate of flow in two different parts of the physics. One is in the Bernoulli's theorem. So there you consider Q as rate of flow of liquid. So it's rate of the volume flow. Okay. So it's AV, the cross-sectional area into the velocity. Okay. And another unit you study a different equation for Q. What's that unit? properties of matter. Whose equation is that?
Yourselves.
Yes, Purcell's equation. Purcell's. Okay, Purcell's. So yesterday also I checked the pronunciation for it. Okay, so 5/8 eta is radius to the power of 4 delta p over L. So can you identify the letters like eta? What's eta here? It's the viscosity.
Coefficient of viscosity.
Yes. Yeah, coefficient of viscosity. Good. What is this?
Radius of the tube.
Yeah, radius of the lumen. What is this as a whole?
Pressure gradient.
Pressure gradient. Okay. Say separately, this is pressure difference between two terminals, and this one is the length of the tube. Okay. So now there is a vessel like this, and from that vessel, water is like flowing like this, and there are two tubes through which the water flows with two different radii, and the pressure differences are given as delta P1 and delta P2, and this is U1 and this is U2. So how are you going to relate these two? So here they are telling that water is allowed to flow. Okay, so when it's allowed to flow, there should be a constant Q. No, otherwise there will be like discontinuity here. So if it is flowing constantly, there should be a stable flow. So Q is equal in those two tubes. So that's the first conclusion that we can come to. So the Q1 is equal to Q2. So here you see the eta, pi, 8, those are constants, and L is also equal. So R to the power of 4 into delta P should be equal to those two tubes. So R to the power of 4 into delta P1 is equal to R to the power of 4 into delta P for 2. So I can write it like this. So they ask you to relate this delta P1 and delta P2 with the velocities. So how can you relate it? So now we have to think about another equation. So that equation is this. So according to the continuity equation also, you have A1 V1 is equal to A2 V2. Okay. So now this A is pi r square. So pi can be cancelled. So R1 squared V1 is equal to R2 squared V2. Okay. So now here you see R to the power of 4. So you have to put it here. So R to the power of 4 V1 squared R to the power of 4 V2 squared. Okay. So now if you divide those two equations, you can cancel R's because R's is the answer instead of the data also. So you never give answers with a new parameter. So just divide it. So V1 squared over delta P1 is equal to V2 squared over delta P2. So now the ratio is delta P1 over delta P2. So if you take this here and put this here, so V1 squared over V2 squared, very easy. Huh? So that is in the third answer. Yeah, the last question is a very interesting question. I didn't do that in my final exam. Okay, because I didn't understand what they are explaining. Now let's try to understand. Okay, so do you have any doubts here in this question? Yeah, it's very easy one. I don't think so. Okay, a particle of mass m is attached to one end of the elastic string. Okay, it's an elastic string. Usually we don't get elastic strings. Okay. So here you have an elastic string of a light, or it doesn't have a mass. Okay, so light elastic string of force constant K and unstretched length of L0, and the other end of the string is fixed to the vertical frictionless wall at y is equal to 0 as shown in the figure. The particle is then projected vertically downwards from the position y is equal to 0 with a velocity of v naught. So they are throwing it. Okay, so it is, so they make a system like this. So there is an object, okay, and there is a string, elastic string. This part of the string is attached to a point which is at the level of y is equal to 0. And they keep this here and they are throwing it like this with a velocity of v naught. Okay, so now let's read. So now let's draw it as it is in the diagram. So it's like this. Okay, so I didn't understand this diagram. Okay, so that's why I couldn't do it. So now the particle is projected vertically downwards from position y is equal to 0 with a velocity of v naught. Neglect the air resistance. After passing through its lowest point in its path, the particle will come again to rest momentarily at a point whose y coordinate is. So you have now, you should be able to explain this motion here. Okay, so now you are going to throw this. So when you throw this, it will freely fall, no? With initial velocity. But from rest, it will freely fall with initial velocity. So when it falls at one point, the unstretched, okay, unstretched string will reach this position. Now it's unstretched. And after this point, it's going to get stretched. Okay. So above this, unstretched. And below this is going to get stretched. Okay. So now if you throw it like that, now it would have reached a very higher velocity because its potential energy was converted into kinetic energy due to the free fall. So at this point, it will have a velocity. And also this string is not going to limit its motion straight away because it can like somewhat stretch. Okay, so that makes the question very interesting. So it will like get stretched. Okay, get stretched. So now what will happen? An elastic string is being stretched. So according to Hooke's law, and practically we all know that when you stretch an elastic material, it's going to first oppose. Okay, it's going to oppose your force, give resistance. Okay, so there will be a tension developed. So for example, if you stretch it by the distance E, the F is directly proportional. The tension developed is directly proportional to E, and F is equal to KE. Those things you know. So due to the stretch, there will be a tension developed, and due to that, the velocity of that object is going to reduce. Okay, that particle is going to reduce. So now the velocity is decreasing. So it's being stretched here. So at one point, when the energy, how do you call it? Elastic potential energy stored in the string equals the kinetic energy at this point, what will happen? It will come to rest. Okay, and you have to consider the vertical height. Okay, I will explain. So at one point, you know, it will come to rest. That's the lowest point at rest. So just find the distance from here to here. If it is given as h, this is h. Okay. So this is x. Okay. This is x. Find x. How will you find? Can you write an equation to find the y coordinate of the lowermost point? So I'm giving you a question. Can you? Yeah. How you can actually apply the law of conservation of energy? So let's start from here. So that is, it has an energy of half mv naught square. Okay, half mv naught square. half mv naught square. So I'm going to take this point as a level of h is equal to 0. So the h will be measured below that level in minus values. No? So here the only energy that it has is this kinetic energy. So what about the energy here? Huh? Can you tell me? Can you tell me? So kinetic energy is 0.
Half kx, yeah.
Yes, half kx squared, excellent. So the stretch is x, so half kx squared plus. You have to put the whole height first step. mg h plus x, but it will have a minus value, no? Minus value. So I put the minus value. Okay, because it's below the level of h is equal to 0. Okay, now you can actually find this x and you can find the y coordinate also. So this is the equation, just for interest, but for your interest. Okay. So what will happen after that? Will it remain there like that? No. Why? Because usually when something is stretched, it tends to come back. Okay, so the kinetic energy that it had, sorry, potential energy stored will be converted into kinetic energy after it passes through the lowest point. And now it will come back. So when it comes back, what will happen at this point when it comes back? Huh? It will cross this level at a velocity which it had when it crossed the same level like this. Okay, there will be no change, because when you apply the law of conservation of energy between these 2 points and these 2 points, you will find that the energy is like interchanged. Okay, interchanged. So at this level, it had a velocity when it went like this, and when it comes again, it will have the same velocity. Okay, then it will come like this. So when it crosses this point, what can you say? It will cross with the velocity of what? V naught again. Okay, so the potential energy was converted into kinetic energy up to this point, and also from this point to this point, and from this point to this point, the total energy was like the kinetic energy was like absorbed by this elastic potential energy, and now it is like released, and it will give the whole energy that it stored as kinetic energy, potential energy again for the kinetic energy, and then it will reach the velocity, the same velocity when it crossed this level initially in downwards direction, and when it reaches this level, it will lose its kinetic energy and it is stored as potential energy. So all the gainings are going to be like given again. I mean, you took that initially and now you are giving it back. So what is the velocity here? V naught. Okay, this is the same velocity that you initially throw it. Okay, same velocity that you threw. So now it will go upwards. So again, the string may limit, okay, may not limit, we don't know. It depends on how much it goes, okay. So if you just consider the free flow, it's not flow, sorry, fall, free fall. If you consider the free fall, you know, the half mv square will be converted into mgh, and h is equal to v naught squared over 2g. So this is the expected height when you consider a pure free fall. It's not falling, it's going upwards, but I'm just telling that for description. So if it goes freely like that, it will reach this height. So we have to check whether it complies with the unstretched length of the string. What is that? Unstretched length of the string? L note, no? L note. And they are giving a very, I mean, you can actually suspect something using that. You can get some idea. Okay, why they are giving that? They are giving the V note less than 2 GL note. What do you think about this? So just simplify this and make L not a subject of this inequality. Okay. Good. Am I correct? I am making this L not a subject. So you can see the V naught squared over 2G is not greater than L naught. So it will not be limited. So it will go up to H, which is V naught squared over 2G. So the question is very simple. So you just have to think about these things for nothing, and then you have to just apply the law of conservation of energy from here to here. That's all. Okay, there is nothing here. It is just conservation of energy. Something is gained and something is given again. So again, when it reaches this point, it's V naught, and it goes freely up to the edge, like you are throwing something without anything attached to it. Here something is attached, but that will not limit. Otherwise, everything is the same. Okay, do you all understand this? It's a very simple question when you understand what's going on. Huh? Do you understand? You can actually use this data as a clue. Okay, so you start to suspect something. They have given this, so something is related to this. So like that, you have to think. So I didn't think like that at that time. I didn't have time and all. So I didn't think like that. I marked the longest answer. I thought it will be correct. I marked 1, but it was the second answer. So do you all have any doubts? So we have finished the seminar. Please forgive my flaws, and I just tried this. Okay, this is the first time I'm doing a seminar for English medium. Okay, so that's all. Thank you very much. Okay, I will upload this video to the YouTube also, so you can watch it. So if I left any mistakes like simplification mistakes, just let me know. Okay, I will include that in the comment section so that anyone who watch the video will not get confused. Okay, so just let's finish. Thank you very much.
Thank you, sir. Jazakallah.
Okay, somebody is asking a doubt. Yeah. Thank you. There are feedbacks. So I may send a Google form, okay, because you conduct any seminar for Tamil medium. Yeah, I'm always conducting seminars for Tamil mediums. I will put that in my YouTube and make sure that you subscribe to it as a help, okay? To my channel Sayati and for Roshan. And share it with your friends, and Sayati has a lot of motivational videos, blogs and all. Usually A-level students like those things. There the numerator and denominator should change. The 25th question, I can't remember how I wrote. Just make sure, okay? Make sure that you wrote everything correctly. Numerator and denominator. Which one? Can you explain it to me? Second answer, no? For the 25th question, 2005. There the numerator and denominator should change. But denominator. I mean, you are telling that I should have multiplied it by k instead of dividing. Okay, let's see the recording on this. Okay, thank you very much. Goodbye. All the best.